Hello, grade 10s, and welcome back to this lesson on electric circuits. We're going to finish electric circuits today. We're going to start off by looking at a circuit construction kit where I'm going to set up a series circuit and a parallel circuit. And as we add resistors in series and as we add resistors in parallel, we will see how that affects the current. If you would like to play around with a circuit construction kit on your own, all you need to do is Google University of Colorado circuit construction, and it will take you to the circuit construction kit website. We're going to do that first, and then we're going to move on to some past paper questions that are in the workbook. So let's begin. We have a circuit with one cell that measures 5 volts. We have one light bulb, that's one resistor, and that resistor measures 10 ohms. So if we're going to close the switch and allow a current to move through the circuit, what would be the current? To measure current, we apply the formula I equals V over R. The voltage was 5 volts and the resistance was 10 ohms. So when we close the switch, we will find that the ammeter reading is 0.5 amps. Here I've closed the switch and I can see that the current is exactly as we'd measured it. It's 0.5 amps. Remember that the voltage across the cell will be equal to the voltage across this individual resistor that we have in the circuit. So the voltage across the light bulb will be 5 volts. Also note that the electrons are moving at a certain speed, and note that the light bulb has a certain brightness. Now I'm adding another light bulb in series. This light bulb also has a resistance of 10 ohms. So what is the total resistance in the circuit? 10 plus 10 is 20 ohms. The voltage of the cell has not changed. It is still 5 volts. So when we close a switch, a current is going to move through the circuit. What we know is that in a series circuit, as resistance goes up, current goes down. So we're expecting to have a lower current in the circuit. Let's do the calculation. We first need to show our calculation for total resistance. So RT equals R1 plus R2, which is 10 plus 10, which is 20 ohms. Now that we have our total resistance, we can work out the current in the circuit. We have the voltage of the cell, so it's 5 volts, divided by 20 ohms, and we get a current of 0.25 amps. So from the previous circuit, we have doubled our resistance. Therefore, we have halved our current because resistance and current are inversely proportional. Let's close the switch. And now we can see that the current is 0.25 amps, exactly as we had calculated. Also note that the electrons are moving more slowly now because that's what current really is. And also note that because the current flowing through the light bulbs is smaller, we have less of a brightness in those light bulbs. We have half the current, so we have half the brightness per bulb. If I had to place the voltmeter across both of the light bulbs, it is going to have the same voltage as the voltage of the cell. If I place a voltmeter across one of the two light bulbs, it will read 2.5 volts. And the other light bulb will also have a voltage of 2.5 volts across it. Remember that these light bulbs are going to share the voltage of the cell equally because those two light bulbs have identical resistances. We now add a third light bulb in series. The switch is open, so there's no current flowing through the circuit. The voltage of the cell is still 5 volts. The resistance of each light bulb is 10 ohms. Again, we've increased the total resistance, so we expect our current to go down even more. The total resistance can now be measured by adding up the resistances of all three light bulbs. So it's 10 plus 10 plus 10, so that's 30 ohms. We can measure the current as V over R, still 5 volts divided by 30 ohms, and that gives us a current of 0.17 amps. So it went down just like we expected it to. Let's close the switch and look at the ammeter reading. 0.17 amps, just like we'd calculated. Note that the current is moving even more slowly, and note that the light bulbs, because they have a smaller current moving through them, are burning with even less brightness. Now let's take a look at the voltage. If I placed a voltmeter across all three light bulbs, I would get the total voltage of 5 volts. Because all three resistors are identical, if I place a voltmeter across just one of the two resistors, I would get a third of the total voltage. 5 divided by 3 gives us 1.67. And it will be 1.67 across any one of these light bulbs. And together, that would add up to the 5 volts. Now that we've looked at a series circuit, let's consider parallel circuit. I'm starting with the original series circuit that has one cell of 5 volts and one light bulb of 10 ohms and therefore a current of 0.5 amps. Now we're going to add another light bulb in parallel. We still have a 5 volt cell. We have two parallel branches. Each parallel branch has a 10 ohm light bulb across it. Now what we learned is that as we add resistors in parallel, the total resistance goes down, therefore the current goes up. So we're now going to work out the total resistance, and then we're going to work out the current, and we expect the current to be higher than the 0.5 amps. The calculation goes 1 over RT equals 1 over R1 plus 1 over R2. So it's 1 over 10 plus 1 over 10. And if you plug that into your calculator, you'll get a fraction of 1 over 5. But that's for 1 over RT, so you need to flip it. So RT over 1 is equal to 5 over 1, which means that the total resistance is 5 ohms. Now we can work out the current as volts divided by resistance. Remember, the cell was 5 volts and the total resistance is 5 ohms, which gives us a total current in the circuit of 1 amp. We're going to close the switch and we're going to see that the current in the circuit is in fact 1 amp. I've opened the switch and I have added an ammeter to each one of the branches. Now remember that the total current is 1 amp. So what do we expect the current across each branch to be? It's going to split, and it's going to split evenly because these two resistors are identical. So when I close the switch, I can see that the total current is 1 amp. It is moving at a certain speed, but then it slows down across each branch. The reason that it's moving slower is because the current is lower. And remember that current is the rate of the flow of charge. It's about how fast are the electrons moving through the circuit. If we had to add up 0.5 amps plus 0.5 amps, we would get the total current of 1 amp. So by adding up the current across each branch, it would obviously give us the total current that leaves the cell and then re-enters the cell before and after the split of the branches. Remember that the voltage of the cell is 5 volts, and if I place the voltmeter across the light bulb on one of the branches, I would get a voltage of 5 volts. And if I placed it across the bulb of the other branch, I will still get 5 volts. This allows us to work out the individual currents per branch. So let's do that. We measure current as voltage divided by resistance. The voltage across each branch is 5 volts and the resistance on each branch is 10 ohms. So that gives us a current of half an amp per branch. Our homes are connected in parallel. So imagine the total current moving through your home is 1 amp, and this is your room, and this is your sister's room, and you both have the lights on in your room. So what you need to realize is that if you turn off the light in your room, your sister's room is not going to be affected. The total current will be affected, but the current moving through your sister's light bulb is still going to be the same. So her light bulb's not going to become dimmer or brighter when you switch off your light or when you turn on your light. So all that happens every time you turn on another appliance in your home is that more total current gets extracted from the mains. The implication here is that if one of the light bulbs on one of the branches burns out, it doesn't impact resistors on other branches, and that is a big advantage of parallel circuits. Let's now add a third resistor in parallel and do all the relevant calculations. Now we have 3 resistors in parallel. So we need to work out their total resistance in order to work out the total current. But remember that by adding another resistor, a third resistor in parallel, the total resistance will go down, so therefore the current will go up. So we calculate the total resistance in parallel as 1 over R1 plus 1 over R2 plus 1 over R3. So it's 1 over 10 plus 1 over 10 plus 1 over 10. And our calculator will give us a fraction of 3 over 10 that we need to remember to flip. So we get 10 over 3. And then we need to provide our final answer to 2 decimal places. So it is 3.33 ohms. We can see that the total resistance has gone down even more the moment that we added a third resistor in parallel. Now we can work out the current as V over R, which is 5 divided by 3.33, and we get a total current of 1.5 amps. Let's go back to the circuit and see that the total current is in fact 1.5 amps. We can see that the electrons are moving quite fast, and then they slow down across the branches because the current splits. It is going to split evenly among these 3 branches. So 1.5 divided by 3 gives us a current of 0.5 amps across each branch. And if we add up the 0.5 plus 0.5 plus 0.5, we get the total current of 1.5 amps before and after the split of the branches. Note also that if I turn off this light, it doesn't impact the brightness of these 2 light bulbs. Remember that by opening one of my branches, I have increased the total resistance and therefore I have decreased the total current. If I turn this light back on, I have decreased the total resistance and I have increased the total current. Because we know that the voltage across each branch is 5 volts, and we know that the resistance of each resistor is 10 ohms, we can also calculate that the current of each branch is 0.5 amps using I equals V over R. So the voltage across each branch is 5 volts, and the resistance of each light bulb on each branch is 10 ohms, and 5 divided by 10 is 0.5 amps, which is exactly what we're seeing here per branch. I hope that this helps in terms of giving you a visual summary of series circuits and parallel circuits. What we're going to do next is go over past paper questions. Consider the circuit below. It's a bit of a weird looking circuit. What we have is 3 light bulbs that are in series with each other, but we have switch 1 over here, and then we've got switch 2, and we have switch 3 that is in parallel with switch 2. Which bulbs will glow if S1 is closed? Well, if S1 is closed, there is still a break in the circuit through S2 and S3. So the circuit's not going to run at all. None of the light bulbs will glow. If S2 is closed, well, we've still got a break in the circuit, so none of the light bulbs will glow. If S1 and S3 are closed, so the electrons will be able to travel through this wire and then through the closed S3. So which light bulbs will glow will be light bulb 1 and light bulb 3. If S3 is closed, again, as long as S1 is open, there's a general break in the circuit, so it will be none. If S1 and S2 are closed, well, the electrons are going to move through S1 and through S2, and all the light bulbs will therefore glow. If S2 and S3 are closed, well, there's a general break in the circuit at S1, so it will be none. And if all of them are closed, then obviously all the light bulbs will glow. Consider the circuit below. Let's take a look at the information we have. We have a 12-volt battery and we have a 6-ohm resistor. There's a voltmeter across the resistor. What do you think this voltmeter will read? There's one resistor in the circuit, so all 12 volts of the cell will be used up by that resistor. Now, because we have the voltage and we have the resistance, we can easily calculate the current. Calculate the ammeter reading. I is equal to V over R, which is 12 divided by 6, which is 2 amps. Because the circuit is in series, we know that the current throughout the circuit will read 2 amps. How much charge passes the resistor in 10 seconds? Now, I find that by this stage, my students have forgotten the two very important formulas of I equals Q over T and V equals E over Q. You tend to be very focused at this point on R equals V over I. However, you've got two more formulas that allow you to calculate current and voltage. We're asked to calculate charge, which is Q, and we were given the time of 10 seconds, and we have current. So the formula is I equals Q over T. We want to work out Q, so we may rearrange the formula as Q equals I times T. So that's 2 amps times 10 seconds, and that equates to a charge of 20 coulombs. What is the voltage across the resistor? Now this requires an explanation rather than a calculation. However, you could do it through a calculation. V is equal to I times R. We know that the current flowing through the resistor is 2 amps, and we know that the resistance of the resistor is 6 ohms. So I times R is 2 times 6, which is 12 volts. But we weren't asked to calculate it, we were asked to explain it. And we know that because there's only one resistor, it will get the full voltage of the cell, because the total voltage is going to be equal to the voltages across all the resistors. There's only one resistor. So that resistor will get all 12 volts. How much energy is transferred by the resistor in 10 seconds? And when you see the word energy, you should immediately think about voltage. The formula for voltage is the energy transferred or the work done per unit charge. Now we already worked out how much charge was transferred by the resistor in 10 seconds, so we have the Q value. We also know the voltage across the resistor, so we can calculate the energy transferred by the resistor. May rearrange the formula as E equals V times Q. The voltage is 12 volts and the charge that we calculated is 20 coulombs. So that gives us an energy transferred by the resistor of 240 joules. The diagram below shows only part of a circuit. We can just see the two parallel branches of a circuit. Now, the one branch has a resistor of 4 ohms and the other branch has a resistor of 2 ohms. The ammeter reading here will measure the total current, and the 3 amps here represent the current on this 4 ohm branch. The first question asks us, what is the current flowing across the branch with a 2 ohm resistor? Now we can't apply a formula here because we don't have enough information to apply any formula. However, the one thing that we do know is that the relationship between resistance and current is inversely proportional. So a higher resistance means a lower current. If I halve my resistance from 4 ohms to 2 ohms, what do I do to my current? I double my current from 3 amps to 6 amps. So we're using ratios here to figure it out. So the answer is 6 amps because current and resistance are inversely proportional. Half the resistance here means double the current here. Calculate the ammeter reading. This ammeter reading is going to read the total current. We have 3 amps on this branch and 6 amps on this branch. The formula is IT equals I1 plus I2, so it's 3 plus 6. The ammeter will therefore read 9 amps. Consider the circuit diagram below. To the diagram, add an ammeter to measure the total current. Now remember that an ammeter is represented by a circle with an A inside it, a capital A, and it is connected in series always. So you can place the ammeter anywhere along the conducting wire. You can place it before the resistor, after the resistor, before the switch, after the switch, before the cell, after the cell. A voltmeter to measure the voltage across the cell. Remember that a voltmeter is represented by a circle with a capital V inside it, and a voltmeter is always connected in parallel. So to measure the voltage across the cell, we have to place a voltmeter above the cell over here. We also have to place a voltmeter across the 16 ohm resistor if we want to measure the voltage of the 16 ohm resistor. We can place a voltmeter across the 8 ohm resistor to measure the voltage across the 8 ohm resistor. And if we want to measure the voltage across both resistors, then we can add a voltmeter here across both resistors that we know, if the switch was closed, would measure 12 volts. And lastly, an arrow to show the direction of the conventional current. If you were just asked to represent an arrow to show the direction of the current, you're automatically going to assume conventional current. You would only show the direction of the real electron flow if that is what is being stated. Remember that conventional current is the wrong direction of the current, meaning that the electrons leave the positive terminal and enter the negative terminal. So you would need to show arrows going out of the positive terminal and entering the negative terminal. When switch S is open, what is the voltmeter reading across the battery? Well, the battery contains chemical potential energy. It is still going to read 12 volts even if the circuit's not connected. What will be the voltmeter reading across the open switch? Well, remember that we learned that the voltage across an open switch is the same as the voltage of the battery, so it will also read 12 volts. When the switch is open, what would be the voltmeter reading across the 16 ohm resistor? There's no current moving through the circuit, so it will be 0 volts. For the rest of the questions, we are going to assume that the switch is closed. What is the voltmeter reading across the battery? Well, open or closed, the voltmeter reading is going to be 12 volts. Remember, we did learn that there's something known as terminal potential difference, which means that the voltage of a cell that is connected in a closed circuit is a little bit lower than its total voltage because some energy is needed to drive the charge out of the battery or out of the cell. But we're going to ignore this effect. If the switch is closed and the circuit's running and I placed a voltmeter across the switch, then it's really just like placing a voltmeter across any conducting wire and it will read 0 volts. Remember that it's not really 0. It might be 0.0001 volts because it does take a little bit of energy for the electrons to move through the conducting wire. But again, we ignore this effect. What will be the voltage reading across the 16 ohm and the 8 ohm resistors together if the switch is closed? Remember that the total voltage will be divided by the resistors and it will be used up in full among all the resistors. So it will read 12 volts across both of them. Let's now calculate the total resistance of the circuit. These resistors are connected in series. So RT equals R1 plus R2. It is 16 plus 8, so the total resistance of the circuit is 24 ohms. Now we can calculate the current in the circuit because we've got the resistance and we've got the voltage. I is equal to V over R, which is 12 divided by 24, which is 0.5 amps. So wherever we place our ammeter, we will get a reading of 0.5 amps. Now that we have the current flowing through the circuit, we're able to calculate the voltage across each resistor. The voltage is not going to divide equally because the resistors are not identical. Remember that the 16 ohm resistor, that's a harder obstacle course for the electrons to move through. So this resistor will get more of the voltage relative to this resistor over here, which is an easier obstacle course. So across the 16 ohm resistor, we may calculate the voltage as I times R. It's 0.5 times 16. And that gives us a voltage of 8 volts. If I connected a voltmeter across the 16 ohm resistor, it would read 8 volts. Now, if I want to calculate the voltage across the 8 ohm resistor, I can apply the same formula. V equals I times R, so it's 0.5 times 8, and that gives me a voltage of 4 volts across this resistor. Note that if we add the 8 volts and the 4 volts together, we get a total voltage of 12 volts, which is the voltage of the battery. This makes perfect sense. Also, if we have the total voltage of the battery and we worked out the voltage across one of the resistors, we can work out the voltage across the other resistor by saying Vt equals V1 plus V2. So the total voltage is 12 volts, and that's going to be equal to the voltage across this resistor, which is 8 volts, plus the voltage across this resistor, which is unknown. So we can calculate the voltage across this resistor by simply saying 12 minus 8, and that gives us 4 volts. Often in circuit problems, there is more than one way of calculating the same thing, and the memo should give you all the different methods. Consider the circuit diagram below. We have circuit 1 and circuit 2. Each one has a 12-volt battery. Each one has a 160 ohm resistor and a 240 ohm light bulb. But in circuit 2, the resistor and the light bulb are connected in series, and in circuit 1, the resistor and the light bulb are connected in parallel. Calculate the equivalent resistance of circuit 2. Equivalent resistance means total resistance. In order to work out total resistance in a series circuit, we simply add up the resistances of the individual resistors. RT equals R1 plus R2, which is 160 plus 240, which gives us a total of 400 ohms. Calculate the current in circuit 2. Now that we have the voltage and we have the total resistance, we can work out the total current by saying I equals V over R. So it is 12 divided by 400. So circuit 2 has a current of 0.03 amps flowing through it. Calculate the voltage across the 160 ohm resistor in circuit 2. So if I want to work out the voltage across this resistor alone, I need to use the current flowing through this resistor, which is 0.03 amps, and the resistance of this resistor, which is 160 ohms. V is equal to I times R, which is 0.03 times 160. So the voltage across this resistor over here will be 4.8 volts of the total 12 volts. Calculate the voltage across the 240 ohm resistor in circuit 2. Now, although this is a past paper question, past papers will never ask you to calculate something in 2 ways. That was just my doing. You would only need to calculate it in 1 way, but I'm going to do it both ways. So one way of doing it is to apply the same formula, V equals I times R, which is 0.03 times the resistance of the light bulb, which is 240 ohms. And that gives us 7.2 volts. 4.8 plus 7.2 must add up to 12 volts, which it does. The alternative is to say Vt equals V1 plus V2. We have the total voltage, and we've just calculated the voltage across the 160 ohm resistor. So 12 is equal to 4.8 plus V2, so that allows us to calculate that the voltage across the light bulb is 7.2 volts. On to circuit 1. Calculate the equivalent or total resistance of circuit 1. Now, these resistors are connected in parallel. So the way that we calculate it is by saying 1 over RT equals 1 over R1 plus 1 over R2. So it's 1 over 160 plus 1 over 240. And your calculator will give you a fraction of 1 over 96. Don't forget that that's the answer to 1 over RT. So we need to flip them both, which gives us an RT of 96 ohms. So the total resistance in the circuit is 96 ohms, which is a lower value than the smallest resistor here, which is 160 ohms. That makes sense. Now that we have the total resistance of circuit 1, and we have the voltage, we can calculate the total current of circuit 1. Remember that the total current of circuit 1 applies to the current before the branch split and after the branch split. I is equal to V over R, which is 12 divided by the total resistance of these two resistors, which is 96 ohms. So we get a total current of 0.125 amps. So that would be the ammeter reading before and after the branches of the parallel circuit. Calculate the current across the branch with the light bulb in circuit 1. We want the current here. We have the resistance of the light bulb, it's 240 ohms. And what is the voltage across each parallel branch? It is the same as the total voltage of the battery. So we have all the information we need to calculate the current through this branch. I is equal to V over R, which is 12 over 240, which gives us a current of 0.05 amps. Now we have the total current, and we have the current across this branch. I'm going to ask you now to calculate the current across this branch in two ways. Let's take a look. One way of doing it is by applying the same formula that we applied to the 240 ohm resistor to work out the current on this branch. I is equal to V over R. The voltage is 12 volts and the resistance is 160 ohms. And that gives us a current of 0.075 amps across this branch. But the alternative is to use the formula IT equals I1 plus I2. We know that the currents across the individual branches will add up to the total current in the circuit. We have the total current, which is 0.125. We have the current across this branch of 0.05. So the current across this branch will be 0.125 minus 0.05, and that gives us the same answer of 0.075 amps. Here we need to consider the current flowing through each light bulb. In circuit 1, the current flowing through the light bulb we calculate to be 0.05 amps, and in circuit 2 it is 0.03 amps. So this light bulb will shine brighter. In this last example, I am introducing you for the first time to a combination circuit. We have a circuit that has light bulb C that is connected in series with light bulbs A and B. So these two components here are in series with each other, but light bulbs A and B are connected in parallel with one another. So let's take a look at how we solve such circuit problems. We were told that the EMF of each cell is 1.5 volts. How many cells do you see here? We've got 1, 2, 3, 4. So that allows us to calculate the total voltage of the battery. Bulbs A and B each have a resistance of 2 ohms, and bulb C has a resistance of 3 ohms. And remember that C is in series with this parallel component. calculate the effective resistance of bulbs A and B. So what we want is the total resistance of this parallel component here. 1 over RT equals 1 over R1 plus 1 over R2, which is 1 over 2 plus 1 over 2. And we get a total resistance of 1 ohm. So together, these guys represent 1 ohm, even though individually they are 2 ohms each. Switch S is now closed. What is the voltmeter reading on V1? Well, V1 consists of 4 cells, each one with a voltage of 1.5 volts. 1.5 times 4 will read 6 volts. What will be the voltmeter reading across V3? I'm going to show you 2 methods for working this out. What we know about the circuit is that this is 3 ohms and that in total resistors A and B add up to 1 ohm. So what is the total resistance in the circuit? It is 1 plus 3, which is 4 ohms. Now that we have the total resistance and we've worked out that the voltage is 6 volts, we can calculate the total current running through the circuit. I is equal to V over R, which is 6 divided by 4, which is 1.5 amps. So now we know that the current flowing through the circuit is going to be 1.5 amps. It's obviously going to split at the branches, but it's going to come back together at 1.5 amps. The point is that the current running through light bulb C is 1.5 amps. So now we can work out the voltage of V3. V equals I times R, which is 1.5 times 3, which gives us a voltage across light bulb C of 4.5 volts. Well, that's one way of doing it. The other way is by working out the total resistance. Again, we know that this is 3 ohms and that these together function as 1 ohm. The total resistance in the circuit is 4 ohms. And light bulb C has 3 ohms of those 4 ohms. So if we consider what 3/4 of the 6 volts is, that would be 3 out of the 4 ohms of the 6 volts, and that gives us an answer of 4.5 volts. So this is really just a ratio method. Light bulb C has 3 ohms of the total of 4 ohms, and so it will get this much of the 6 volts, which would equal 4.5 volts. We also need to measure the voltmeter reading across the parallel component. And I'm going to show you 3 ways of doing this. So one way is, again, using the ratio method. V2 will have a reading based on the total resistance of A and B, which is 1 out of the total of 4 ohms in the circuit, times the 6 volts of the cell, so it will get 1.5 volts of the 6 volts. If we add up 1.5 plus 4.5, we will get 6 volts, which makes sense. Alternatively, we can say V1 is equal to V2, which is unknown, plus V3, which we've just calculated, so that the total voltage of 6 volts is equal to V2 plus 4.5, which gives us an answer of 1.5 volts again. And the last method is to apply the formula V equals I times R. We already calculated the current, and even though the current splits at the branches, we know that the total current among both of the branches would be 1.5 amps. And we know that the total resistance across both of these resistors is actually 1 ohm. So 1.5 times 1 gives us a voltage of 1.5 volts. Calculate the energy transferred in light bulb C in 3 seconds if the current in the circuit is 1.5 amps. For this kind of question, you need to recall these two formulas. I equals Q over T and V is equal to E over Q. And we're asked to work out the energy transferred. For that, we need the voltage across light bulb C, which we have, and we need the current, which we don't have. So we can't work with this formula quite yet. We are not able to calculate the energy transferred quite yet. We're missing the Q. If we come to this formula, I equals Q over T, we were given the current, we were given the time of 3 seconds, so that allows us to work out the charge. Once we've worked out this charge, we can come back to this formula. Given the voltage and having calculated the charge, we can work out the energy transferred. So let's take a look. I equals Q over T. I've rearranged the formula as Q equals I times T because we're trying to figure out the charge, Q. That is 1.5 amps times 3 seconds. So the charge that is being transferred through light bulb C is 4.5 coulombs. Now that we have the charge, we can come back to this formula to calculate the energy. V is equal to E over Q, and I've rearranged this formula as E is equal to V times Q. So that is a voltage of 4.5 volts that we calculated earlier, times the charge of 4.5 coulombs, and our final answer will be an energy of 20.25 joules that's transferred in light bulb C. And lastly, all the light bulbs are now connected in parallel. How will the total current in the circuit be affected? Will it increase, decrease, or remain the same? Provide a reason. So we're going to take light bulb C out of its series slot and add it in parallel. By removing a series resistor and adding it in parallel, what are we doing to the total resistance? Total resistance will go down. So what will happen to the total current? The total current will go up. And that's because resistance and current are inversely proportional. So the answer will be increases. As more resistors are added in parallel, the total resistance will decrease. So the current will increase because resistance and current are inversely proportional. That brings us to the end of the section on electric circuits.